Hello, my dear students, and welcome. Today, we are going to learn a very important topic from your Unit 13 on nuclei. Now, I know the moment you hear nuclear energy, it sounds very difficult, very complicated, right? But I promise you, by the end of this short explainer, you will find it is bilkul simple and very logical. So let's get started and make sure you are 100% ready for your exams.
Okay, so to understand nuclear energy, we have to start with a very interesting puzzle. Just imagine the nucleus of an atom. Think of it like a tiny room that shouldn't even exist. Now, think about this for a second. Inside this tiny room, you have all these protons, right? And what charge do protons have? Positive! So you have all these positive charges squeezed together in an incredibly small space. Now, you all have studied Coulomb's law. You know that like charges repel each other. They should be pushing each other apart with tremendous force. So the big question is, why doesn't the nucleus just fly apart? Why doesn't everything just explode? What is this super strong force that's holding it all together? This is the mystery we're going to solve today. And the answer to this puzzle, well, it's a little bit strange. It's one of the biggest secrets in physics, actually. And it all comes down to something that seems to disappear, something that goes missing whenever a nucleus is born. Let's think of it with an analogy. I call it the marriage paradox. See, in our world, if you take two things and combine them, the total weight is just the sum of the two parts, right? Simple. But in the world of the nucleus, something very weird happens. When protons and neutrons come together, when they get married to form a nucleus, the final nucleus is actually lighter than all the individual protons and neutrons were by themselves. It's like some of their mass has just vanished. How is that even possible? Well, the key, my dear students, is probably the most famous equation in all of science. You know it. It's from Albert Einstein. E equals mc squared. And what this simple formula tells us is something incredible, that mass and energy are not separate things. They are two sides of the same coin. They can be converted into one another. And this formula shows that even a tiny amount of mass can be turned into a huge, enormous amount of energy. Now, for your exam, this is very important. You have to use the correct scientific term for this missing mass. It is called the mass defect. We use the symbol delta M for it. The definition, straight from your textbook, is simple. It is the difference between the mass you should have, by adding up all the protons and neutrons, and the actual mass you measure for the real nucleus. And please remember this crucial point. This mass is not destroyed. So here it is, the big reveal, the answer to our puzzle. That mass defect, that missing mass, it hasn't just disappeared. No, it has been converted into a massive amount of energy. And we call this energy the binding energy. You can think of it like a super strong cosmic glue. This binding energy is the force that holds the nucleus together so tightly that it easily overcomes that repulsion between the protons. This is what keeps the nucleus stable and stops it from flying apart. Let's make this crystal clear with a very simple example. Let's take a helium-4 nucleus. It has 2 protons and 2 neutrons, okay? Now, if you take a calculator and add up their individual masses, you get a total of 4.03188 atomic mass units, or U. But when scientists actually weigh a helium nucleus, its real mass is only 4.00260 U. So the difference, our mass defect, is just 0.02928 U. Now that number looks very small, doesn't it? But watch what happens when we use Einstein's formula. That tiny mass converts into 27.3 mega electron volts of binding energy. That is a huge amount of energy at the atomic level. Okay, so we now know that creating a nucleus releases energy. But how can we know which atoms are stable and which ones are not? Well, for this, physicists have a very beautiful and useful tool. You can think of it like a roadmap for nuclear energy. Now, please pay full attention here. This graph is straight from your NCRT book, and it is extremely important for your exams. This is the binding energy per nucleon curve. The rule to read it is very simple. The higher an element is on this curve, the more stable its nucleus is. And if you look carefully, you can see the peak of the curve, the highest point, is right around the mass number 56. And which element is that? It's iron. That's why iron is one of the most stable elements in the whole universe. So a good way to think about this is that every nucleus in nature has a goal, and that goal is to become more stable. It wants to climb the hill on this graph to get closer to the peak where iron sits so comfortably. This means that elements that are very light on the far left of the graph and elements that are very heavy on the far right, they are both less stable. And both of them can release energy if they can find a way to move towards that stable. Now, this natural tendency of every nucleus to climb the stability hill gives us the two most powerful and famous processes in all of nuclear physics. So let's compare these two paths. On one hand, you have fission. This happens with the very heavy guys, like uranium, who are on the right side of the curve. They are too heavy, so they split apart into two smaller, lighter nuclei. By doing this, they move up the curve, become more stable, and release a huge amount of energy. This is exactly what we use in our nuclear power plants. Then you have the opposite process, fusion. This is for the very light nuclei, like hydrogen on the left side of the curve. They combine or fuse together to form a heavier nucleus, like helium. They are also climbing the curve, just from the other side. And in doing so, they also become more stable and release an unbelievable amount of energy. This is the process that powers our sun and every single star in the sky.
All right, everyone, I need your full attention here, please. We're now going to talk about some very common exam mistakes. I call these the silent killers because they can quietly make you lose marks if you are not careful. So let's make sure you don't fall into these traps. So, first question. Think about it. True or false? A heavier nucleus, one with more protons and neutrons, is always more stable and stronger. The answer is a big false. This is a very common misconception. So many students think bigger means stronger, but in the nuclear world, it is the opposite. Just remember that stability curve. Where was the peak? It was around iron. The really heavy elements, like uranium, are actually unstable and radioactive. So please remember this line for your exam. Heavy nuclei are like radioactive bombs, not strong fortresses.
Okay, second silent killer. In a nuclear reaction, when energy is released, is mass actually destroyed? Yes or no? The answer is a huge no, and listen to me very carefully. In your exam paper, you must never, ever write that mass is destroyed. This is a critical concept. Mass is not destroyed. It is converted into energy. Which energy? The binding energy. And it happens according to E equals mc squared. The total amount of mass plus energy is always conserved. Please remember the word converted, not destroyed.
All right, we are almost at the end. Let's do a super quick revision of the most important points. These are the things you absolutely must remember for your exam.
So let's go. Point number 1, the nucleus is held together by the strong nuclear force, which comes from the binding energy. Point 2, the mass of a nucleus is always less than its parts. This is called the mass defect. Point 3, this missing mass is converted into binding energy. Point 4, energy is released whenever a nucleus becomes more stable, whenever it climbs that hill. And finally, point 5, fission is splitting heavy nuclei and fusion is joining light nuclei. I suggest you pause the video here and maybe take a screenshot of this slide for your notes.
And you see, this is why this topic is so amazing. What we learned today, it's not just some theory for your exam. These ideas explain some of the most fundamental things in our universe. They explain how our sun gives us light and heat every single day through fusion, and they also explain how we generate electricity for our cities through fission in nuclear power plants.
And so, I will leave you with a final thought. Our sun runs on fusion, right? It's an incredibly powerful process, it's clean, and its fuel, hydrogen, is everywhere. Right now, the best scientists in the world are trying to build a fusion reactor here on Earth. Just imagine for a moment if they succeed. If we can control the same power that fuels the stars, right here on our planet, what could humanity achieve with clean, almost limitless energy? Something to think about. All the very best with your studies.